Welcome to this lecture of graph theory. In this lecture, we shall discuss the Peterson's theorem about one-factors, and the theorem states that every cubic graph without cut edges has a one-factor. Before starting the proof of the theorem, we shall recall these definitions. We have used a definition like a cubic graph, then cut edges, and one-factor. Now, first of all, a cubic graph means a graph in which every vertex has degree 3. So we have this cubic graph. This is a graph having a graph in which every vertex has degree 3. Now, second definition that it is using a definition cut edge. So this is defined as an edge of a graph G is a cut edge if this G minus this edge E is disconnected. So if a graph G has an edge E whose removal from G leaves the graph G disconnected, then we call that edge E as a cut edge. Now the third definition that we are using here is a one-factor. One-factor means this is a perfect matching. Perfect matching means a matching in a graph G is said to be a perfect matching or a one-factor if this matching contains all vertices of G. So these are the three definitions that what we are using in the statement of Peterson's theorem. This theorem now again states that every cubic graph without cut edges has a one factor. Now let's proceed towards proving this theorem. So this is the proof. So let G be a graph and having no cut edge, and let S be a subset of vertex set of G, and moreover, and let this like O1, O2, so on, OK be the collection of all odd components of G minus S. We want to show that G has a one factor. So in order to show G has a one factor, we show this number of odd components in G minus S is less or equal to order of S. And then we can use Tutte's theorem and use Tutte's one-factor theorem. So this is our idea of the proof, and we know that the Tutte's theorem states that a graph has a one factor if and only if the number of odd components in G minus S is less or equal to order of S for every S contained in vertex set of G. So here we just need to show that if we choose any subset S from the vertex set of G, then the number of odd components in G minus S is less or equal to order of S, and then Tutte's theorem will conclude the proof that the graph must have a one factor. Now for this, let's consider an ith odd component. Consider the odd component OI. So let's consider the odd component OI for I equal to 1, 2, so on up to k. Now let's have some notations. Let OI has ni vertices, mi edges whose both ends are within OI, and let there are ki edges from OI to S. So we are making three different classifications here. Now first of all, let's construct the component OI here for some I from 1 to n, 1 to k. So, and here we construct the set S whose removal from G leaves these k odd components. Now it is possible that the vertices of OI are adjacent within the vertices of OI, and they may be adjacent with some vertex of S. These are the only two possibilities for the adjacencies for the vertices of OI. So the only possibilities for the vertices of OI are either the vertices of OI are adjacent within the vertices of OI, or they are adjacent to some vertices of S. So this is OI. Now the possibilities is that the vertex can be adjacent within OI, and it may be adjacent like this, or now the other possibilities is that this vertex may be adjacent to some vertex of S. And similarly, there is some other vertex like here, which is adjacent with some vertex of S. And now the total number of edges that have both ends within OI, we denote that number by Mi. So Mi is the number of edges whose both ends are within OI. And Ki is the number of edges that have one end in OI and the other end in S. And this situation is true for every OI. So here we note these details. So first of all, vertices of OI are either adjacent within OI or adjacent to vertices of S. And we have the notation that order of OI is Ni. Then obviously Ni is odd because this is an odd component. Now Mi is the number of edges within OI and Ki is the number of edges from OI to S. Then we have the following things. So then we have, let's first of all compute this quantity summation V belongs to vertex set of OI degree of V. So we shall compute the total degree of the component, odd component OI. Now this can be defined as, first of all, this is the total number of edges which are within OI. So this is equal to twice the number of edges which are within OI. So this is twice the order of edge set of OI. So if there are some edges within OI, then they will contribute 2 to vertex degrees. So every edge will contribute 2 to the vertex degrees. So total number of edges within OI will contribute 2 times the number of edges within OI. But there may be some edges from OI to S, and that number is already defined to be equal to Ki. So actually we mean to say here that this summation V belongs to OI degree of V, this is equal to twice Mi plus Ki. Now this equation gives us, this implies this Ki, this is equal to summation V belongs to vertex set of OI degree of V minus twice Mi. So now this further implies Ki is equal to, now since our graph is a cubic graph, therefore every vertex has degree 3, so that means every vertex in OI will also have degree 3 in G. So therefore this is equal to 3 times the number of vertices in vertex set of OI minus twice Mi. So this implies this Ki is equal to 3 times Ni minus 2 times Mi. Now here in this situation, this Ni is odd. So now here Ni is odd. So here note that Ni is odd and this 2Mi is even. Here Ni is odd because this is the order of an odd component OI. So this implies, and so we have this Ki is also odd. Because now if this Ni is odd, then 3 into Ni is odd, and odd minus even number is an odd number. So that means Ki is an odd number. But now what is our Ki? Ki is actually the number of edges from OI to S. So hence the number of edges from OI to S is equal to odd number of edges. Now this odd number can be 1, this can be 3, this can be 5 and so on. But now since our graph does not have any cut edge, so there cannot be exactly one edge from OI to S. Because otherwise, if there is exactly one edge from OI to S, then the removal of that particular edge will leave the component OI separated from G. So in other words, that means that the removal of that particular one edge will leave the graph G disconnected. So that is a contradiction to the fact that the graph does not have a cut edge. But now here, since G has no cut edge, thus this Ki is not actually 1, but this is greater than or equal to 3. Now when Ki is greater than or equal to 3, this means that there are at least 3 edges from every OI to S. So that means there are at least 3 edges from O1 to S, then there are at least 3 edges from O2 to S, and so on. So when there are at least 3 edges from OI to S, that means every OI contributes at least 3 degrees to the total degree of S. So this means that each of I contributes at least 3 degrees, at least 3 vertex degrees to the total degree of the vertex set S. Therefore, if we define this quantity, suppose we want to define summation degree of V, where V belongs to a vertex set of S. Now this will be greater than or equal to 3 times the total number of odd components, and we have assumed that the total number of odd components is equal to K. So 3 times the number of odd components is less or equal to the total degree of S. Now this means, so this implies this K is less than or equal to 1 divided by 3 summation V belongs to vertex set of S degree of V. But now the graph G is a 3 regular graph because it is a cubic graph, so every vertex in S will have degree 3. So therefore this is equal to 1 divided by 3 into 3 times order of S. So this finally implies this K is less or equal to order of S. But K is the number of odd components in G minus S. So this implies K naught of G minus S is less or equal to order of S. Hence by Tutte's theorem, one factor theorem, the original graph G has a one factor. So this completes the proof of this Peterson's theorem.